in this lecture, we will be defining what is meant by a connectedness in digraphs. Okay. Now, let me first recall what we know in the case of an undirected graph. Okay. You know what is an undirected graph? A graph in which the edges are not or edges do not have any direction. Okay. And now if you look at this, if I take a graph like this, okay, if I take a graph like this, somewhat like this, u, v, w, x, y, z, then I have a and b. Okay, this is a connected graph, because what is meant by a connected graph? I can move from one vertex to other vertex. Okay, so this is called as a connected graph. Okay, and the characterization of a connected graph is this: if I have a path between any two vertices, then such a graph is said to be a connected graph. Now what I have to do is, I have to define the connectedness in the digraph, and what I have to do is, relevant to this path in the undirected graph, I have to define what is meant by a path in a directed graph. So all those things are being discussed, in this particular lecture. So our aim in this is to define a connectedness in a digraph, which is a directed graph, which is also called as a directed graph. Okay. So before moving into the connectedness, okay, you have a relationship between a binary relation and the directed graph. Okay, and the directed graph. Okay, the first part I will give you how to construct a directed graph for a given binary relation. Okay, now I will first define what is a binary relation. Suppose if I take a relation, take a set x1 consisting of elements x1, x2, x3, so on, xn. Okay, I take R as a subset of x cross x, Cartesian product x cross x. Okay, what is this x cross x? X cross x is the set of all elements xi comma xj. Okay, such that xi comma xj belongs to x. It can also be same. Okay, so in this case, what happens here? This is called as a Cartesian product, and your relation, this is called as a relation, and this relation is a subset of x cross x. You have a special relation, what you call it as the equivalence relation. Okay, you have a special relation called as an equivalence relation. What is this equivalence relation? It should satisfy three properties, namely reflexive property. It has to satisfy the reflexive property, and number two, it has to satisfy symmetric property. Okay, symmetric property. And the third one is, it has to satisfy the transitive property. Transitive property. What is this reflexive property? X is related to x for every x in x. Okay, x is related to x for every x in x. This is called as the reflexive property. And what is symmetric property? X is related to y. This should imply y is related to x, and this has to be true for every x and y in x. And now the third one, what is third one? X is related to y and y is related to z. This should imply x is related to z. This is true for every x, y and z in x. This is called as the transitive property. And an equivalence relation is a relation which satisfies these three properties. Now, what we will be doing is, we will be constructing an equivalence graph. Constructing an equivalence graph. Okay, I'll just take an example and I will define what is an equivalence graph. So now what I do is, I take the relation like this: addition modulo 3. mod 3, okay, or it is also denoted by plus 3. What do you call this? This we call it as addition modulo 3, okay, this is called as addition modulo 3. Now what I have to do is, I will take the integers from 10 to 20, okay, my set is from 10 to 20, this will be your set x, okay. So x would contain elements 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, you can see that it has got 11 elements, 3 plus 3, 6 plus 4, 10 plus 1, 11. So now what I do is I can see that x comma r, okay, is an equivalence relation. Okay, that is this relation R, which is defined as addition modulo 3, is an equivalence relation. So now what I do is I draw like this 10, I will have 13, 16, 19. Okay, so now if you look at this, 10 is related to 13, 13 is related to 10. So I will have two edges, one like this. Similarly, 10 and 19 are related. I will have two edges, one edge will be in the direction opposite to this. Okay, obviously you can see that 16 minus 10 is 6, divisible by 3, divisible by 3, and similarly 10 minus 16 is minus 6, which is also divisible by 3, divisible by 3. So now I have an edge. Now if you look at this 10, 10 minus 10 is equal to 0, which is also divisible by 3. So I will have a loop here. Okay, so similarly 19 minus 19, 16 minus 16, 13 minus 13, these are all divisible by 3. So I have the graph or one part of the graph. Okay, so now I can remove this 10, I can remove 19, I can remove 16, I can remove 13. Now let me start with 11, then same I will have 14, I will have 17, then I will have 20. Now I will have this, I will have two edges, okay, because 11 is related to 20, 20 is related to 11, 11 is related to 14, 14 is related to 11, 14 and 17 are related to each other, 17 and 14 are related to each other, 20 is related to itself, 17 is also related to itself, 14 is also related to itself, and 11 is also related to itself. So now what I do is I remove 11, 14, 17 and 20. And now when I take the remaining one, I have like this will be 12, 15, 18. As done earlier, I will have two edges, okay, I will have two edges, and 12 is related to itself, 18 is related to itself, and 15 is related to itself. So this will be the digraph, okay, this would be the directed graph which is associated with a relation. Here I have taken an equivalence relation, okay. If you have a relation that itself is sufficient, you can just draw a graph using it. Okay, so the first one is constructing a graph, directed graph for a given relation. Okay, so now I will move to the next part, what you call it as the directed path and connectedness. Directed path and connectedness. Okay, so I will explain this using this example here. Okay, I will take an example, more E5, this one will be U2, E4, U1, I have two edges, this one is E2, this one is E3. The direction is important here, this one is E7, U4, U5 and U3, this one is E1, E8, this one is E9, this one is E10. Okay, so now you have a graph like this. Okay, so now what I do is I define a directed path. Okay, what is the directed path? Okay, directed path here is U5, E8, U5, E8, U3. Okay, U3, E6, E6, U4, E3, U1. Okay, this is a directed, okay, this is a directed path. Okay, this is a directed path in the sense that from U5 I can go to U3 via E8. Direction is specified. From U3 I move to U4 through E6. Direction also coincides. From U4 I go to U1 through U3, E3, the edges. So this is called as a directed path. Now I also have a path like this. If you look at this, U5, E9, U3, E1, U1. Okay, this is a U5, U1 path. Okay, now if you look at this particular edge E1, okay, I am moving against the direction of E1. Still, it is a path when I take a undirected graph which is associated with this directed graph. So, such type of path is called as a semi-path. Such type of path is called as a semi-path. So, now in the case of a directed graph, you have two types of paths. One is called as the directed path, where the directed path is a sequence of vertices and edges. Okay, sequence of vertices and edges, whereas the edges should follow a direction. So if I take E8 which is given here, okay, the tail of E8 should be U5 and head of E8 should be U3, or from U5 I have to move to U3 through E8. So I cannot violate the direction that has been given in the edge. If I am able to find, a directed path, or if I am able to find a path, then such a path is called as a directed path. Now I am ignoring the direction of an edge and I am finding a path for the corresponding undirected graph that is associated with it, then such a path is called as a semi path. Okay, so this is the first part that you have to remember. The next one would be a directed walk. Okay, what is this directed walk? Okay, from a vertex, okay, it will be like this, from a vertex ui to uj, okay, is an alternating, we have like this, is an alternating sequence of vertices, and edges, okay, beginning with ui, and ending at uj, and each edge is appearing only once, okay. So this is called as a directed walk. Okay, if I ignore the direction, then I would have a semi walk, then there I would have a semi walk. Okay, similarly I have a directed cycle, okay, or I would have, okay, a semi-cycle, semi-cycle. Okay, now you can see this for this graph U3, E6, U4, E3, U1, E1, U3. This is a directed cycle. Okay, from U3 I move to U4 through E6. From U4 I go to U1 through E3, and from U1 I go to U3 through E1. So I have started with U3, ended with U3, so that would be a directed cycle. But now when I take this graph, sorry, take this cycle U5, E7, U4, E2, E1, U3, E9, U5. This is a semi-cycle. Okay, because in some cases I would be moving against the direction of the edge. Say for example, if you look at this edge E9, I would be moving against the direction. Instead of moving from U5 to U3, I will be moving from U3 to E9. So that will be called as the semi-cycle. So in this case, with respect to this directed graphs, I will have two types of definition. One will be called as the directed path or directed circuit or the directed walk. The other one would be the path, circuit and walk associated with a undirected graph corresponding to the given directed graph. So that one is called as the semi walk, semi path and semi walk. Okay, so those things are to be remembered. So when you talk about digraphs, you have two different paths that you have to consider. The next one, what we do is we define what is a connected digraph. Okay, we define what is a connected digraph. Okay, what is a connected digraph? Here I have two types. One is called as the strongly connected digraph. Okay, one is called as the strongly connected digraph, and other one is called as the weakly connected digraph. Okay, weakly connected digraph. So now what you have to do is you have to see that what is meant by a strongly connected digraph and what is meant by a weakly connected digraph. Okay, a graph. Okay, by a graph I mean a directed graph. A directed graph is strongly connected. Okay, this you say it as a strongly connected if there is a directed path. Okay, if there is a directed path between any two vertices. Okay, so that is called as the strongly connected digraph. And now you would have guessed what is meant by a weakly connected graph. Okay, a directed graph, okay, is weakly connected. Okay, is weakly connected if there is a path. Okay, if there is a path between any two vertices in G, any two vertices in graph G. Okay, similarly in graph G. Okay, so now what happens here is that no directed path. Okay, no directed path. So obviously it should have a semi path. Okay, so that is called as the weakly connected digraph. So you have two types of connectedness in the case of the directed graph. One is called as the strongly connected digraph and the other one is called as the weakly connected digraph. Okay, so now we will define what is meant by a component of a digraph. Component of a digraph G. Okay, So now what is meant by a component of a digraph G? Maximal connected, okay, maximal connected subgraph, okay, maximal connected subgraph of a directed graph G, of a directed graph G is called a component of G, is called a component of G, okay, and within each component a maximal strongly connected subgraph is called a fragment, is called a fragment. So in this case, again in the case of the undirected graphs, you have two things. One is called as the component, okay, but here you have two types in the directed graphs. One is called as the component in general, the other one is called as the fragment. So in this case, what happens here is that with this fragment, you can also construct another strongly connected graphs. So in this case, you have to remember the definitions, and you should also remember the example of a component of a digraph G. Okay, let me explain this concept of fragment and connectedness using this example. For this, you consider this graph. Okay, let me draw a graph like this. This one would be E14, E11, and E13, E12. Okay, this would be G1, E1. Here I have E2, E3, E5, E4, okay, E10, E9, E7, E8, E6. This would be G2. Okay, this would be your G2. Okay. Now let me write down here G1 and G2 are components. Okay, G1 and G2 are components. Okay, and the component, okay, the component G2 has three fragments. What are the three fragments? You can see here what are all the three fragments. One is E10. Okay, E10 is one. The next one would be E5, E6, okay, E7, okay, E7 and E8. Okay, you can see a directed path E5, E6, E7, E8. E10 is another fragment. Now when I move to the next one, I will have E1, E2. So E1 and E2, so it has got only three fragments which are given here. And now using these three fragments, I can create another graph by condensation, called condensation. Okay, this is nothing but a transformation of the graph. Transformation of the graph. So now what I do is I take this is E1, E2 as one vertex. I create each fragment as a vertex. The next one would be this, what is that, E5, E6, E7, E8, and the last one would be E10. Okay, now if you look at this, from E5, E6, from E5, E6, E7, E8, I have an edge. I have an edge joining E2, E1, E2 in the direction from E1, E2 to E5, E6, E7 and E8. So I have a directed edge like this. And similarly from E5, E6, E7, E8, I have an edge. Okay, I have an edge. This will be your E9. Okay, this would be your edge E9. But of course, here mentioning this would be meaningless. So you have an edge. So this, if you look at this, this is what shall I say? This is called as the condensation of the given graph G. This is called as the condensation of the given graph G. So in this case, you have to remember what is meant by a component, which is a maximal connected subgraph, and if it has a directed path or if it is strongly connected, then such component, maximal component, is called as a fragment, and using this fragment you can transform the given graph, what you call it as the condensation of the given graph G. Okay. So now what we do is we define accessibility. Okay, accessibility. Now you can see the word accessible. It is clearly understood here. What is this accessibility? If U and V as a directed path, okay, directed path, then V is accessible. Okay, V is accessible from U. U is accessible from U. Okay, so now you have this important result, which will be very simple here. Okay, a directed graph G, a directed graph G is strongly connected. A directed graph G is strongly connected if and only if every vertex, okay, every vertex in G, every vertex in G is accessible from every other vertex, every other vertex. Okay, so this would be a strongly connected, and of course this would be easier. Okay, if and only if condition. What is meant by this if and only if? So now what I do is I assume that G is, proof would be like this, very simple. G is strongly connected. Okay, when G is strongly connected, what do you have? You have, there exists a directed path from one vertex to every other vertex. Okay, what is the meaning of it? Which implies that every vertex is accessible from every other vertex. So in this case, this happens every other vertex. So one vertex is accessible to every other vertex, so I am able to get this. And now when you look at this converse is also very simple. Every vertex is accessible from every other vertex. What does this mean? This means that there exists a directed path. Okay, what is that? There exists a directed path from a vertex to every other vertex, So this would be the definition of you are strongly connected, which implies that G is strongly connected. G is strongly connected. So in this case, these are certain important definitions and notations that you have to remember, which we will be using in future. So now let me recall what we have done in this particular lecture. We had defined what is a directed path and semi path. Okay, and similarly we had defined what is a cycle and what is a path. Okay, number 2, what we did was we defined what is a strongly connected graph. Okay, this was the second part that we had defined. Number 3, we had defined what is meant by a condensation of a graph. Okay, what is meant by a condensation of a graph? That is nothing but a transformation of the graph. Transformation of the graph. Transformation of the graph. And number 4, we characterized strongly connected, okay, strongly connected digraph. We had characterized strongly connected digraph, but at the beginning we had constructed a directed graph for a relation defined on set X. Okay, so this was done in this particular lecture. If you have any doubts in this, you can post your queries at venkatakrishtu at max.sastra.edu and I will be answering your queries. Thank you.